Welcome to lesson 7.2. This is the second lesson for chapter 7, where we're talking about population ecology and population dynamics. So learning objective here is that you will be able to describe the different factors that can limit population growth, as well as different reproductive strategies. So we're focusing on population limits, and then we'll talk a little bit about how different species reproduce, or different strategies they use for reproduction. All right, so factors that limit population size. We've talked about this a little bit, but factors that prevent unlimited population growth are known as limiting factors. They limit the growth. All of the different limiting factors that act on a population are collectively known as environmental resistance. Remember, a population is all of the individuals of one species. So our community is all of the different species, all the different living things. When we're talking about population, we are talking about one species specifically. So environmental resistance is every limiting factor that acts on that species. There are two different kinds of limiting factors that we're going to talk about. There's going to be extrinsic limiting factors, and those are the ones that come from outside of the population. So it could be predators. So obviously, like if we're looking at a mouse population and it's living in a wooded area of foxes, foxes are going to go after the mice. And so that would help limit that population of mice. A loss of a food source. If a food source goes away, then there's more competition for that food within the population. So again, within that one species, which means less individuals are going to be able to survive. It could be lack of sunlight. We could be talking about plant life, or also there are like living creatures also need some light. And then it could be accidents of nature. So a wildfire that goes through an old growth forest, that is an extrinsic limiting factor because it came from outside of the population, but it still is going to limit that population. So if it's not extrinsic, it's going to be intrinsic. So intrinsic limiting factors are those factors that originate within the population and exercise control over it. So examples could be behavioral changes amongst the population that can cause lower birth rates and higher death rates. And then there's also density-dependent limiting factors. And those, these are ones that become more effective as the density of the population increases. So this doesn't necessarily mean as the population grows, although that can definitely cause it. It just means that if the population is more dense, they live a lot closer together, it's going to impact them more. If it's not density dependent, then it will be density independent. These are population controlling influences that are not related to the density of the population, and we will go over examples of these. So for most populations, limiting factors recognized as components of environmental resistance can be placed into four main categories. It's either raw material availability, energy availability, accumulation of waste products, and then interactions among organisms. So if it's raw material availability, that's going to be, it could be like food availability, it could be water, it could be light. Energy availability, that would also be food, it could be sunlight for plants. Accumulation of waste products, if the population is huge and really dense, a lot of organisms living in one place, and things are dying and excreting waste and all the things, and that habitat is no longer going to be a healthy, clean place for them to live, and so that's going to impact how many can live there. And then interactions among organisms could be like predation and those symbiotic relationships. So an example of accumulation of waste products, we're looking at the number of bacteria over time, and this one is going to be hours. So we looked at our growth curve in our last lesson. So here's our lag phase, exponential growth, deceleration, and then it's stable. But because there was so much waste accumulated over that time, the bacteria after about 44 hours ended up dying off because it was no longer a habitable place for them to live. So all of these limiting factors lead to what is called a carrying capacity. And a carrying capacity is the maximum sustainable population for an area. It is not an inflexible number. It can be influenced by environmental differences. So again, one ecosystem does not have a solid set carrying capacity that is the same every moment of every day, of every month, of every year, of everything. It is impacted by external effects as well as things that are happening within the ecosystem. So that can change from successional changes as we're going through succession into those different stages in succession. It can support different organisms, so that carrying capacity could go up or down for different species. It could be influenced by climate variations. It could be influenced by disease epidemics, forest fires, floods, or natural disasters, and also nutrient levels in aquatic ecosystems. So if we look at these, some of these are extrinsic, some of them are intrinsic. So if we look at like disease epidemics, and we were talking about it being density dependent or density independent. If we live really, really close together and lots of people in small spaces, disease epidemics are going to have a greater impact versus populations that are more widely dispersed. So disease epidemics would be an example of that could be intrinsic because it's coming from within the population and it's density dependent. Forest fires, floods, or natural disasters, that would be an extrinsic limiting factor because it's coming from outside the population, and it's density independent. It does not matter how close or far apart you live. That forest fire is going through that forest, it's going through the forest. All right, so here is a visual of that carrying capacity and how the limiting factors or environmental resistance are holding that carrying capacity down or that population down. So here we're looking at, we'll say, salmon in an aquatic ecosystem. So we have our lag phase here, our exponential growth phase, and then it evens out. And what's causing it to even out is all of those limiting factors pushing that population down. All right, so the second part of this lesson was talking about reproductive strategies and then population fluctuations. Not every species reproduces with the same strategy. So species can be divided into two broad categories based on their reproductive strategies. There are K strategists and there are R strategists. So K strategists are organisms that typically reach a stable population as the population reaches the carrying capacity. R strategists don't ever like stable out for a long period of time. They tend to be small organisms that have a short life, produce a ton of offspring, and exploit unstable environments. They do not reach a carrying capacity. And we'll look at those each specifically. So for K strategists, they usually occupy relatively stable environments. There's not a lot of change happening. They tend to be larger organisms. They live longer than most R strategists. They produce a few offspring comparatively. They provide substantial parental care. They're not just popping out a new baby and then it's on its own. And the reproductive strategy is to invest a great deal of energy into producing few offspring that have a good chance of living to reproduce. They are controlled by density-dependent limiting factors. So when we looked at those density-independent versus density-dependent, K strategists tend to be more influenced and controlled by density-dependent limiting factors. So how big that population is and how close they live together is going to influence how much they can survive with those limiting factors. R strategists' characteristics include they're small, short-lived organisms. They produce a lot of offspring, little, if any, parental care. They exploit unstable environments. They usually do not reach carrying capacity. They go through a boom-bust cycle. And then the reproductive strategy is to produce a ton of offspring to overcome the high mortality. So they're having a ton of offspring knowing that sometimes 90, 95, 99% of them will not make it to reproduce on their own. R strategists tend to be controlled by density-independent limiting factors. So because they have so many, it doesn't matter how spread out they are, those limiting factors are going to, the density-independent limiting factors are going to be the ones that affect them more. So this is what their growth curve would look like versus humans, who are K strategists. We had that lag phase, exponential growth, and then it evens out. R strategists, exponential growth, and then they crash because most of the offspring are not going to make it to reproduction. And then the ones that do reproduce have a ton, and then they crash, and that repeats over time. So I'm not going to read every single one on here, but here's a really quick comparison between the two with some examples. So I want to point out, for example, for K strategists, it's not like we said big animals. Some plants also can be considered K strategists. Are they taking care of their young? No, but they meet all of the other point. And then the last little bit we're going to talk about is population cycle. So a lot of animals show a distinct population cycle, which are cycle periods of relatively large populations followed by periods of small populations. So it doesn't necessarily mean one thing or another. It just is a natural back and forth. But maybe this looks just like that R strategist graph that we just looked at. All right, that is the end of this lesson. Please let me know if you have any questions, and I will see you in the next one.